Okay, so first chapter, what was the first chapter? The first chapter was ranking cycle, right? So ranking cycle is also a vapor cycle. It functions based on the vapor. So we modified this cycle, pretty much actually almost all cycle we modified from the Carnot cycle, right? So for this cycle we learn, let's see, we write the Carnot cycle. So let's say we have ES diagram. So originally Carnot cycle looks this way. Something like this. So Carnot cycle. But we say that this cycle is not practical. Does anyone remember why this is not practical? That is definitely one reason. But then a lot of your calculation you also assume reversible, right? So what are the main reasons? I mean, there are a few reasons actually behind this. So we look at process 1 to 2 first. So why is 1 to 2 not practical? The main reason for 1 to 2 not being practical is, no, actually when you solve you also assume I say profit. One of the main reasons is because it is not practical to design a pump that works with 2 phases. Because we either have a pump that works with pure liquid, or we either have a compressor that works with pure gas. We don't want them to work with a mixture of gas and liquid. So if you follow the original Carnot cycle, 1 to 2 actually works in a mixture phase, which is something that we don't want. So 2 to 3 technically is doable, but it limits the temperature, it limits it limits TH basically, the high temperature, or it limits the temperature of heat addition. Because pretty much we learned that actually the higher the temperature of heat addition, the more efficient the process will be, the more energy we also can generate. So that is also the issue. So then process 3 to 4, the reason that it is not doable, pretty much similar. Actually doable also, but high moisture content, which leads to the corrosion of turbine blades. Four to 1 no issue, so there are no right. 4 to 1 is just condensation. So in order to make this thing practical, what we do is basically we try to solve all these issues, the 1, 2, 3 that we mentioned. So for 1, we move this all the way to the left, so that we move 1 to 1 prime, so that now we don't have the issue of dealing with 2 phases. We only want to deal with 1 phase, which is liquid phase here. And 2 to 3 again we say is doable, and so 2 becomes 2 come over here. So 2 to 3 we say it is doable, but it kind of limits the temperature that we have. heat at, because it's an isothermal temperature process. So now, usually at OH, not OH lah, but initially actually this is fine. Most people will go with this because 2 to 3, 3 to 4 is not really not doable. It's just not good. Right. But of course, these days we don't do that anymore. So what we do is we superheat this all the way to 3 prime. And this solves both issues at the same time. So you get to add heat at a high temperature, and you get a very low moisture content at the exit of the turbine. So by doing this, you solve both issues at the same time. And so what you get here is Rankine cycle. And for this Rankine cycle, this part, so you get Q in over here, you get Q out over here, you get work out here, and you get work in. So after studying about open system, we know that each of these work out, work in, Q out, Q in, we can find them through the difference in the enthalpy, pretty much, or enthalpy of each of the states. So in this case, the only exception here, not really exception, but there's the only one that we make a bit more assumption here would be state 1 to 2. So I will only show that one. The rest is just a change in enthalpy. So at state 1 to 2, we say that work in, or maybe I write the small letter one like this here. So we say work in is equal to H2 minus H1, or to be more accurate, we use prime here. But we also know that we can assume V as a constant at V1 and P2 minus P1. So this is another thing that you need to bear in mind. The rest is also, they are all H. So they all revolve around finding what is H. And then you have your thermal efficiency, which is rho max over QP, or 1 minus QR over QE. Can still write one. I cannot press a bit. Okay, so then we have 2 different modifications. Please. Yeah, 2 modifications to Rankine cycle. The first one is the reheat cycle. So for reheat cycle, it is pretty much the same thing, just that we reheat it 1 time. So 1 to 2 to 3. So at 3, it goes over here. And we come down here. So we get 4, 5, 6. And so here, same thing, Q out, Q in, but you have another Q in here. you have 2 workouts. So you need to remember you have 2 workouts, 2 cube in. I didn't realize I didn't talk about ideal versus actual. That one I think I assume you guys know. So these are all ideal. So, okay, maybe just very quick one. So if you have an actual one, then the only difference is, so 4 will change, 2 will also change. So same thing for this one. So if you have an actual one, then you will have this thing, this extra one, and you need to use or find, I'm using isentropic efficiency. So this is a release cycle. And then the other modification that we have is the regenerative. This is the complicated one. So we have regenerative ranking cycle. For regenerative ranking cycle, we have 2 types also: open feed water or closed feed water. Calculation wise, in general, we don't really ask you closed feed water. This one, the most is just the theory. So for open feed water, it looks something like this. So initially it's pretty much the same. The only difference is that when you reach 3, go all the way down, right? We open another path. Oh wait, I shouldn't draw it this way. So let me draw it. Okay, so maybe we start from 3, okay? So from 3, to 4, we open another path here. So here 1, 2. So we send some of the vapor from 3 back here. So here you get another 3 to 4, 6 to 8, 5, 6, 7. Okay, so for this, what you need to remember is that at this point, they split. So coming in here, let's say you have 1 kilogram per second. So here it will split to either y and y minus 1 percentage. So one thing that you need to, this is what you need to remember for this. So, and then they meet back at 3. So 6 to 7 to 1 to 2, you won't have a full amount of the water because they got split. So you only have y amount. The y amount is the fraction that goes over there. Okay, then we go to chapter 2. Chapter 1 pretty much is all this. So, chapter 2, we have Brayton cycle, which is also a gas power cycle. So for this Brayton cycle, Brayton cycle is a gas power cycle. We make the air standard assumption. I won't go into detail what they are, but you have to know. So we use the air standard assumptions. Basically, we just assume the whole thing is air. There's no combustion involved. Because as you can see from the previous chapter, if the combustion is involved, then coefficient is very troublesome. So we assume there's no combustion, just air. Okay, so Brayton cycle, what we have here is, okay, maybe draw the whole thing. So you have a compressor. So this one we have a compressor. It goes to a combustion chamber. And so you take in air, then it goes to a turbine. And here is exhaust. So it is actually an open cycle. So if we draw this TS diagram, so one important thing to remember about Brayton cycle, this is a gas power cycle, meaning there is no condensation, there is no evaporation, so you don't draw saturation line for this. So all you need to draw for this is very simple, just two lines. So you have two constant pressure lines. These are the two constant pressure lines. So, okay, maybe I draw following this diagram first. So initially you have 1 to 2, so this is 1, 2, 3, 4. So this is a work-in process. This is the fill-in process. So until 3 comes out. To 4. So open system or open cycle pretty much looks just like this. But of course this way is a bit hard to solve for us. So by using air standard assumption, we assume that this becomes a closed system. So meaning we close this whole thing up. So then you get another constant pressure line, then it goes back this way. So it is like an imaginary cooling device or something like. It's just that this is the entire atmosphere. That's all. We can actually go there. So this is the Brayton cycle, or the simple one. Of course, if you are looking at an actual Brayton cycle, then same thing here, then you get a 4 prime. So for Brayton cycle, we have two methods. One is constant specific heat method, or the other one is variable specific heat. So most likely constant specific heat method, we just use the constant specific heat value at 300 Kelvin. And so for constant specific heat, maybe we take one example. So Q in, let's say, is Cp, T3 minus T2. But variable specific heat, then Q in will be H3 minus H2. So this one you use table A17. This one we use equations. And for the isentropic processes, for constant specific heat, we use T2 over T1 equals to T2 over T1, K over K minus 1, I think so. K minus 1 over K. So always remember, this process, you only can apply this if you are dealing with isentropic process, ideal gas, and constant specific heat. So for the variable specific heat case, then you just assume P2 over P1 is equal to PR2 over PR1. Again, you use table to find this value. You also learn a new thing here, which is called backward ratio. So backward ratio is basically just work in over work out. So how much work is being used to power the compressor from the turbine. Okay, then now we look at the modification. For this one, in the lecture I split into two, but pretty much technically there's only one full modification. So the main one will be here will be, let's say we look at regeneration. So regeneration is actually the same as the previous one. Right, so TS so 1, 2, 3, 4. You just add one more here, over here. So 5. Of course, this is the ideal one. The actual one maybe go somewhere about a bit lower, so 5 prime. So here you have another term, which is effectiveness, I think. Yes. So effectiveness would be just how effective is the basically effectiveness is how effective is this regeneration. Regeneration, no spelling. So how effective it is how much heat it can heat it up before you need heat addition. Because Q in is over here. So which is why this will be just H5 prime minus H2 over H5 minus H2. And we know that for air or for gas, temperature is the one that decides everything. So if temperature never changes, this is actually the same form. For constant specific heat, you also can say this is just this one. Okay, so then now we look at the last modification. Oh, I ran out. Which is intercooling and reheating. So for intercooling and reheating, maybe we split into two parts. So basically this whole thing is so regeneration is to improve efficiency. Intercooling and reheating is actually to improve backwork ratio. Okay, so what happened here is this. So if we look at the compressor, rather than just heating it one time, cooling it one time, so compressing it one time up, we compress it one more time. So here we get 3 and 4. Before it goes to the heat addition process. So usually we keep this at the same level. So that T1 equals to T3, T4 equals T2 equals to T4. So this is the intercooling. If we look at the turbine, which is the reheating part, then this is the same as what you learned in the previous chapter. We heat it up to, let's say 6. Then we cool it down. Then we let it go through the turbine one time. Then we reheat it again, 8. Then we cool it down one time again, 9. Before, again we cool this down. So once again, these are supposed to be at the same level. So T6 equals to T8, T7 equals to T9. So, if we put this entire thing into the TS diagram, so pretty much what you can do is just to make sure they are at about the same level. So 1, 2, 3, 4. So here also same thing. So this is how it goes. So usually, we also know that if we only implement these two, RPW will increase, but efficiency will reduce. So in order to counter this, then we will usually just add in a regeneration here. Here, the number that I use is slightly different from my notes because I use like my own number. So we will also introduce regeneration in order to counter the drop in the thermal efficiency. So if you do something like this, then so this will be your Q regen. This is your Q in. This is also Q in. This is work out. This is work out. Q out. Q out. Work in. Oh, sorry. Off here. So by right here, you will have, so this will be Q region also. And this is Q out. But usually this one, the region, to avoid confusion, we don't use Q out. We stick to one out, one in, it's easier. Okay, so this is where I stop. Tomorrow we will enter new chapter, and for 1 minute, because 1 hour class. Then next Monday also new chapter, then next Tuesday test. So next Tuesday still got lab? No, only last lab. Quick 11.
Replace my replace up 11 Only some kaya naman may open na replacement. Replace the 拍四吗？拍四Next week
有啊，OK 啊。Got your don't come.
有诶。
菠菜面要买